Okay, and moving on, Tarik will continue on this theme of the challenges of associativity and commutativity. So please take it away whenever you're ready.
Okay, mic check. Perfect. So I will basically continue where we left off, but we have a bunch of differences. I'm Tarik Rosin, and this was work done at Saarland University together with Marcel Ullrich and Sebastian. So many of us view an E-graph like this as a visual, as a graph, but there are a bunch of different perspectives on the same data structure. I inserted the term on the left into the E-graph, and if we now, for example, try to apply associativity to it, we would insert the new pattern match, the new expression, and unify it at the root to the existing one. And now the different perspectives would be, if we label the E-classes as well, we can write it as a term rewriting system, which rewrites to the E-class IDs. So the E-class IDs are essentially part of our original theory as just basically constants. And another perspective on the same data structure would be as relations, where this is the relation only for the multiplication operator. So we left out the inverse, and as you can see, it's essentially the same, just in a different notation. We will be using both of those variants interchangeably, and when I say an E-node, I mean either a tuple in the database or one of the rewrite rules in the term rewriting system. Okay, so how do we generally match patterns in an E-graph? We've seen this in the previous talk. We use query algorithms. This was prior work by Zhang. And essentially, when we have a pattern like this one, we lower it to a flattened representation, where we always insert like a E-class ID, a root element, to link the flattened atoms together. And then we have the leapfrog algorithm, or the generic join algorithm, which we already saw previously. In order to make it efficient in just traditional E-graphs, nothing with AC yet, we store the relations as tries. So we take all the tuples and we just insert them in the trie like this to share the prefixes. Then how the algorithm proceeds is, at each stage we compute all candidate values that the variable x can take, and we do this by looking at the current level, taking the intersection, and in this case the intersection is only the E-class ID A. So next up we would loop over all candidates and restrict our data structure to just the path where A was chosen. So A is fixed. Next up we would repeat this for all the variables. And there's a small trick we can do for the roots, or in general for the roots of an atom. We don't need to loop over all candidates because there's a functional dependency from, in this case, x and y towards the variable r. Intuitively speaking, if you know the E-node, multiply x by y, then you can look up the ID in the hash table we already use for hash consing. So you don't need to store this even in our relation, in our tries. We can reuse this interning or hash consing table to find the one value, the one unique value, and no E-node is contained in two different E-classes. We will be using this later. Okay, and then after we have considered our candidate, we need to walk up the trie again. So this gives us the trie cursor interface, where we have a few functions which are basically required to implement this traversal. The first and kind of most important one would be select, which in this case is just follow the edge you selected. Unselect is walking it back up, walking back up to the parent. Keys would be to get all different outgoing edges at the current node. And then contains and the size are mainly needed to implement the set intersection. Okay, moving on. In traditional eGraphs, we store our data like kind of like this. And in a multiset eGraph, if we now want to bring AC into the picture, we can flatten it together like in the previous talk and have just one multiset representation, one variadic representation for all the nodes that were in here. And this also allows us to have a canonical representation for an already AC saturated eGraph. In here, this part of the eGraph is not even saturated yet, so it's leaving out a few E nodes. And the database representation would be this one. And notable, we only do this for the relations, for the operators that have the AC property. The others we leave untouched. Okay, so what changes about pattern matching? We compile the pattern to kind of the same lowering, but we introduce a new formal variable. The purpose of this is to differentiate multisets, which we'll see in the next slide. If we want to implement the tricursor interface now for this kind of relation, we would instead, when selecting, remove the key from the multiset once. And when unselecting, we just put it back into the multiset. The keys are essentially the support of the multiset, so all the unique elements. And containment and approximate size are, again, self-explanatory. So what do we need this T for? Namely, if we look at the original algorithm, in order to use the tricursor interface as I just presented, we need to have only one multiset at a time, which we can index into. And we introduce this T to select which multiset we are using. So it's an outer for loop around the pattern match, which goes through the multisets one by one. And it's opaque to the users. They don't have to know about this. And the concrete values also don't matter. It's just to separate. Okay, with this, we would again take the same intersection, but this time remove A from the multiset. And the same goes for Y. But now we have a bit of a problem. Namely, in traditional eGraphs, every subterm is represented. Every subterm is contained in the eGraph. If we now try to look up the multiplication between A and E3 in the hash cons, there is no entry for it, so it has no E-class ID. And we don't want to allocate E-class IDs during matching, just freely. So what we do instead is we create ephemeral, so-called ephemeral E-class IDs. These exist from during matching until when we apply the pattern, so when we insert the other side of the pattern. Yes, and essentially they just have one bit flipped, and we have to store the e-node associated with each ephemeral e-node until we have figured out whether we want to keep this as a match or not. Okay, so this was about matching, but the equality saturation algorithm consists of a few parts, namely also congruence closure or rebuilding. And there is actually a very rich existing literature on algorithms. There's one by Kapoor, which we will be using, and it works as follows. So the first step is to mark you focus on a single relation at a time, and you mark all e-nodes in there as unprocessed or as dirty. Then you take a single one and you update it, you canonicalize it with a union find. Then you simplify this one e-node you selected with all the already processed e-nodes to maybe shrink it. Now comes the complicated part. You take your simplified e-node and you take you compute all critical pairs between the clean e-nodes you already have. We see in a second why this is necessary. Okay, and last but not least, we inter-reduce all the clean e-nodes with a new one we are adding to the set of clean e-nodes. And we repeat, we go back to step 2 if we still have dirty e-nodes left. So let's see an example of that. If this is our small set of e-nodes, we have to choose, we already marked them as dirty, so we now have to choose one arbitrarily. Let's just pick this one. There is no union find right now that modifies it. There's also no clean e-nodes which can simplify it. So there's also no clean e-nodes with which we can compute critical pairs, so we'll just add it over here. And let's repeat. Now let's pick this e-node. And here there's nothing to canonicalize, there's nothing to simplify. To be precise, by simplify I mean using the rewrite rule on the right to simplify the right-hand side of the rewrite rule over here. But it doesn't match, so now we have to compute the critical pairs. In this case, these two have a non-trivial overlap, namely A, and we can create the ground MGU like this, and then we have the property that it one time rewrites into E2 times E3, and one time it rewrites into E4 times D. These two are new e-nodes that were not present in the previous eGraph, and but they break the property that it canonicalizes. So we unify them by just adding a rewrite rule that makes these two equal. Okay, so we add these two rewrite rules with a newly added E5, and we are done with processing this one. All right. Okay, so I think you get the gist. Here are some results. The memory savings are, I would say, very significant because we don't store all the subterms. We get away with storing only, or oftentimes only, one canonical representation. So, for example, in this case where we multiply A 10 times by itself, it adds nothing. It's basically free. And one counter example is up there. H is here supposed to be a homomorphism. Okay, so in some cases we save up on space asymptotically, and in many cases it's constant or linear in space. However, it's not all that great because at the same time the algorithm is not complete for pattern matching. Let me give you an example. Here we have AB and we have the A inverse pulled out, right? So if we apply pattern matching on this, we would find that A via E3 gets cancelled. However, if we were to first apply congruence closure, we would factor out the A times B, and now, because our algorithm scans over a single multiset, we are no longer able to see that A is in connection to the A inverse, because our algorithm doesn't iteratively unfold or something like that. And yeah. Okay. And then there's maybe the question whether, even if it doesn't work all the time, does it at least save memory all the time? And here the answer is also more nuanced, because the homomorphism case is an unfortunate counterexample. What happens here intuitively is that we wrap the H around every variable. And this causes all subterms to be materialized and be stored. So the advantage we get from storing only one representation or only one canonical representation is lost. And furthermore, we perform worse than traditional equality saturation in this case, because In egg or egglog, you store the nodes as binary, and with this we also will have all the ternary variants and all the arity 4 and so on. Okay, so to conclude, there's a lot of future work to make this really efficient, and maybe a question is, when is it efficient, or how much is the effect of completeness, or how devastating is the effect of the missing completeness, and can we extend this to other theories by implementing the tricursor interface? And last but not least, we have not talked about extraction. So depending on your cost function, extraction might be even the harder problem. Okay, credits to these 2 papers for implementing half of what I presented. And that's it.
Does this always terminate? Does the AC congruence closure part always terminate?
Yes. So in the paper by Kapoor, he's using, I think, Dickinson's lemma to prove that the congruence closure algorithm does terminate. Any other questions?
I have a quick question. I mean, you mentioned that part of the reason why on some of these degenerate cases you perform worse than conventional equality saturation is this subterm materialization issue. One of the things that Phil mentioned in his talk is, he said intuitively certain of these, in his was a different setting with these redundant terms. He was talking about how these are not interesting or not likely to be interesting to many applications. I'm wondering, how do you, I'm sure you've thought about, in terms of future work, how do we make progress in this subterm materialization question, assuming that in most cases, many of them are probably not interesting? How do we make sense of that?
Okay, I would kind of disagree. I think there are cases where you have an interesting rule like a homomorphism, which is useful, so you need to think about it. One option is maybe to extend it to other theories. So maybe you have AC plus homomorphism, and you have a data structure for that. It's not the most ergonomic solution to always extend your EGRAPH implementation to your theory, but it's probably the most straightforward. Yep.
Okay, then let's thank the speaker one more time.